Welcome everyone to Boise State Physics First Friday Astronomy event. I'm Brian Jackson. You're tuned in, of course, to the First Friday Astronomy event. For those of you who have never joined us before, these are events hosted by the physics department here at Boise State, and they happen on the first Friday of every month. So the first Friday of every month, 7:30 p.m. Mountain Time, we invite some kind of a space scientist, maybe a space policy expert, to come out and give some kind of a lecture on their research or space science topic of interest. These happen on a monthly basis and they are entirely donation supported. So if this is something that you're interested in, if you want to bring more space science to Boise, please help us support this program. You can donate at boi.st/give-to-astronomy. That helps to support this program. Our talks, as I say, happen every month. And the next talk that we're going to have is scheduled for October the 1st. I want to show you this presentation's poster because it's going to be really exciting. We're going to have Dr. Yaoyuan Mao of Rutgers University come to speak to us about dark matter, the invisible nests of galaxies. So that'll be really fascinating. I think you'll enjoy that a lot. For tonight's lecture, we invite you to ask questions using YouTube's chat feature. Let me see if I can show you where that is. Here you can see the live stream, and on the right-hand side over here, you can see the chat feature. And so if you have a question for our speaker, please put it here, and I will happily relay it to our speaker. You're welcome to ask questions all throughout the talk, and I will relay them all at the end. So you should have a lot of luck getting your questions answered. If you cannot hear, of course, you can see that I'm masked. Our speaker is going to be masked. If you cannot hear, please indicate that you can't hear in the chat window, and I'll make sure that we can increase the volume for you. Okay. And with all of that, I'd like to welcome our speaker, Dr. Lori Fenton. Dr. Fenton is a research scientist at the SETI Institute in California. She earned her bachelor's degree in physics and astronomy from the University of Minnesota, followed by a PhD in planetary sciences from the California Institute of Technology. She was then a postdoctoral research assistant at Arizona State University and joined the SETI Institute, where she studies planetary geomorphology and aeolian processes. I think she's got a really great talk prepared for us tonight. And with that, I'm going to stop talking and turn it over to Dr. Fenton.
Hello there. Can everyone hear me? Please let us know if you do not hear me. So, let's see if I can share my screen. I can't share my screen.
Oh, you can't. Give me 1 second.
Try it again. Oh, there we go. Okay. How do I do the desktop? Sorry.
So when you click share screen, you should have the option of sharing your desktop or sharing the app.
Yeah, I see it. Oh, there it is. Sorry. This is my first talk. My first talk in a mask, certainly.
Yep.
Yep. Excellent. So let me make this bigger so it's cooler. There, did that work? No, I'm in this. Nope, that did work. Perfect. Okay, awesome. All right, well, I'm going to be talking about dust devils, and I titled this talk Details on the Devils because that's what I'm trying to find. But I want to first say that I'm not talking about the biblical kind of dust devils, so please, I hope I don't offend anybody. I'm talking about the kind of dust devils that you find out in the desert that pick up dust and whirl it around. It's just what we call them. And before I start, I want to point out there's a long list of names on the left here. The top is a group of people who've been working with me to study these dust devils. But along the way, we have picked up a couple of students, one graduate student and a number of undergraduates.
Advance your slide one slide real quick because it's showing this subtitles thing on top of your slide.
Oh, it shows up there? Remember, it wants me to turn it on, but I don't want to turn it on. There's no way to turn that on. It's that orange. Oh, there it goes. There it goes. Okay, perfect. Awesome. Okay, so, and we have some undergraduate students that have come out in the field and really helped us analyze the data. And I want to give a shout out specifically to Justin and Ryan here at Boise State, because they came out to help us this year in the field, and they've helped analyze the data afterwards. And without them, our project wouldn't be what it is. So thank you so much for doing that. And also thanks to Professor Brian Jackson, for inviting me to talk here and for letting his students come out in the field and help. So I'm going to talk a little bit about the kinds of projects that I have worked on over the years, so you get a feel for what I do. Everything kind of boils down to the same thing. I study how wind on any world out there, any planet, any moon that has an atmosphere on it, how that wind interacts with the surface and changes the surface. So things like sand dunes, which you see on your lower left, that's a Mars sand dune that's slowly advancing forward over time. We can look at how the wind moves the sand, and the shape of the dunes can be used to figure out what the wind patterns are. And from that, we can learn about the weather on a place like Mars or in a remote place on Earth. So it's a really interesting thing. We can also look at how the wind sculpts the surface, how it erodes the surface. And on the top left, you'll see a dust devil. This is a dust devil on Mars, and I'll show you plenty of dust devils on Earth, so don't worry. So, oh, how do I do? You're seeing it on Zoom? You're not seeing it here. Okay, how do I get out of presenter mode? My presenter view? Is that better? It looks better on my screen. I'm sorry. Okay, awesome. Okay. So where was I? Okay, so let's just move on. The top middle is a map of Mars. That's the globe. You're seeing topography. Blue is low and orange is high, and all of the little yellow dots are dune fields on Mars. So those are just wind-blown sediments that have piled up and been streamlined and sculpted by the wind. And I was part of a group that went and mapped all the ones on Mars so that we can then use that as a platform to launch other studies. So let's see, the middle on the bottom is part of a study I'm working on right now with Matt Choniaki from the Planetary Science Institute. There are dunes like the one on the lower left of the screen that have been sitting on Mars for a very long time, and they have become like the bedrock. They've become lithified. And so they get hardened, and then they get eroded over time by more wind. And so we're looking at those because we want to try to figure out what the weather patterns were like on Mars a long time ago, like 1 billion years ago. And on your lower right, what you're seeing is an overhead shot of the Mars wind tunnel at NASA Ames. So I'm part of a couple of studies that's looking at how if you put sand in a wind chamber on Earth and lower the atmospheric pressure down to like Mars-like pressures, then you can learn something about how sediment is transported on a world like Mars. But I wasn't always a planetary scientist, so I thought I'd give a little background to where I started. So I was always interested in astronomy as a little kid. And at some point, my parents saw this and bought me a really, really cheap little telescope for maybe Christmas, I don't remember. And I was very excited. My dad took me out to the backyard and he pointed it at a star. And I was excited to look at a star through the telescope because they're just points of light if you look with your eyes, but surely it must be more interesting if you look through a telescope. And it looked like what you're seeing on the left. It wasn't really any more interesting. But then he pointed it at Saturn. And that's what you're seeing on the right. Saturn, I could see had a disk and it had rings around it. And even more interesting, if you look really closely, if I could kind of look out of the corner of my eye, I could see that there was a little dot and that was a moon of Saturn. And it just blew my mind. So from then on, in some way, I've been a planetary scientist really at heart. And yeah, I know that there are stars that are worth looking at in little telescopes too. I've learned that since then, but it's too late. I became a planetary scientist. Okay, so I continued to do well in math and science in school, and then I went to the University of Maryland for college, where I studied physics and astronomy, and I got an internship at NASA Goddard Space Flight Center, which isn't too far away from the university, where I worked with a team that studied the atmosphere of Mars. They were working with the TESS instrument, the thermal emission spectrometer, which looks at infrared light that comes from the planet of Mars. Really, that instrument was designed to look at the mineralogy of the rocks of the surface, but all that light has to pass through the atmosphere too. So there was a group of atmospheric scientists who were trying to understand what the atmospheric structure of Mars was like where is there dust in the atmosphere? Where is there ice? And so I was part of that group when I was an undergraduate. And they gave me my very first research project of my own. And that's what you see on the right over here. So they didn't tell me to work with tests, or this is before I was global surveyor really got to Mars, but they didn't really want me to work on with the proto data, if you will. But instead they assigned me a mission that happened before I was even born. That's the Mariner 9 mission. That was the first spacecraft to orbit a world other than the moon or Earth. So it went out there to a planetary body and it orbited it. And it got to Mars in 1971 in the middle of one of the biggest dust storms that Mars has ever experienced. And so they didn't even turn the camera on for a while because they knew this was happening and they knew that they would just see just a dusty ball. But as time went, the dust receded a little bit. And so what you're seeing here is a picture of the three of among the tallest volcanoes on Mars. They're about 15 kilometers or more tall. So there's a lot of dust hiding everything below that. You're just seeing the very tips of the volcanoes there. So that's what I studied, the decay of that dust storm. And from then on, I was interested in Mars. And so let's see, I'm going to show you, I'm going to show you a couple of movies. You can see it? Okay, perfect. Thank you. I want to see which ones I wanted to show you. Okay. So I'm going to show you what a dust devil is because I'm going to be talking about those a lot. So this is from our first field season. This is just at our base camp looking at a really cool dust devil off in the distance. And you can see people there for scale. So you can see that this is a really big thing. And I'm tilting up into the sky because it's really, really tall. This thing is, I don't know, 20, 30 meters across, maybe a couple hundred meters away. And I don't know how many hundreds of meters high in the air. These things are huge. And the thing I want you to notice, I'll show you another video after this one, is how blue the sky is. There's not a lot of weather going on. There's just perfect fair weather. And yet in the middle of it, there's this beast swirling around, moving across the horizon. Why? Why does it do that? You know, I'll get into that in a little bit. We'll watch this thing, it's heading off, and then it's going to kind of dissipate a little bit. Still tall. All that dust that gets lofted, it just stays up there. Well, let's look at the other one. This is similarly from our base camp. But these, I think, are even bigger dust devils. They're off in the distance. They're moving really slowly. They look like they're moving slowly, at least because they're just so big and so far away. And again, just perfectly clear blue skies. There's two of them. I'd say those are, I don't know, several hundred meters high. I don't know how wide, maybe 100 meters wide. It's really, really big, and I would say majestic, but maybe I'm biased. All right. Oh, and I wanted to show one last video, because videos are awesome. This is a numerical or computer simulation of a dust devil, because there are groups around the world that are trying to study dust devils. And I just thought this was a really beautiful illustration of what they look like. So you can see that they're swirling around and they're picking up dust from the ground. This one moves around, and towards the end of this, you'll see this little satellite swirly forming towards the left. Here it is. Here it comes in, right there. That happens in real life. You can see little ones circling around the bigger ones sometimes, getting caught up in them. So amazing. Okay. So, let's see if I can again. Oh, I'm in presentation mode again, aren't I? There we go. Okay, so before I can tell you what a dust devil is and what it's doing there in the middle of this beautiful blue skied weather, I have to tell you something about what we call the planetary boundary layer. So you may have heard about the troposphere, which is the lowest layer of Earth's atmosphere. That stretches up to 10 kilometers. This diagram says 11 kilometers. That's about the height at which a jet airliner will fly. Within that, there are other layers, and the lowest layer is called the boundary layer because it's the boundary between the Earth and the atmosphere. And you can think of it as the layer in which most weather happens. It's the layer in which pollution gets trapped, dust gets trapped. Most things you think of in terms of the atmosphere happen within the boundary layer. And it's because it's so important to our lives, it's something that a lot of people want to understand. And it stretches from anywhere like 100 meters or so high up to a couple of kilometers high. So that boundary layer has a typical characteristic behavior on a nice clear day without any other weather. If you're in the desert and you have a nice flat plain and there's nothing else going on, this is kind of what happens. So let's see, let me find my cursor here. Okay, so here's time off on the horizontal axis, and here's height up here. So the sun rises, it shines through this nice clear air onto the surface, it warms the surface, and the surface gets hot, much hotter than the air above it. And because there's this contrast in temperature, that can cause the air to convect. And that means there are these circulation motions that form. And as the sun gets higher in the sky, it heats the surface even more. The circulations get more vigorous and bigger, and they start to form what's called a mixed layer, or sometimes you might hear me call it a convective boundary layer, or a CBL. That thing forms and grows to fill up the entire boundary layer over the course of the day. And at some point in there, when it gets pretty tall, that's when dust devils start to form. And it's really just these convective motions that are creating what we call vorticities, so swirling motions that sometimes get tilted into the vertical. And if they get strong enough and they touch the ground and there's loose dust on the ground, then it's going to get picked up, and that's why you see it. All of this is going on in free, beautiful blue air that you can't see, all these swirls. So if you're standing somewhere and you feel these gusts buffeting you every now and then it gets quiet and calm, and then you get buffeted again, that's what you're feeling. So here's another perspective. Rather than looking at it as a matter of time, let's look at it in space. So there are convection cells happening within this convective boundary layer. So let's see. If you're looking at it kind of like you were looking out of an airplane window down at the boundary layer, you have, think of big convection cells where you have air that it wants to form a sphere. And those two spheres, if they bang against each other, they form an upwelling wall of warm air. That's what these are right here. These are walls of warm air trying to rise. And where three or more of these cells bang against each other, you get vertices. So it's like they turn into polygons instead of spheres, because they're kind of squishing against each other like bubbles. And this is where air kind of gets drawn into this one spot that really gets a lot of energy and raises up high into the atmosphere. It's called a thermal. And that is where any ambient vorticity, any swirlies get merged together. And that's where you tend to find dust devils. So looking at this from above, here's an output from a numerical simulation. So this is taken at a height. So if you were to slice through the atmosphere at about this height and look down, this is what you'd see. So the red is air that's moving upwards, and the blue is air that's moving downwards. And so at these walls where these cells meet, so like right along here, this is where you have air that's rising up, and at the vertices, that's where the dust devils form. So like right here, or here's an even better one. So that's at a height of maybe 100 meters. So let's go down. If you go down to about 10 meters, that's within these cells. There's even smaller cells inside the bigger ones. They get stacked. So in this simulation, they found swirlies, nice things that might become dust devils. And they marked them as these yellow spots here. So numerical simulations can produce something like dust devils, and we think that's how they're produced out there in the world. Okay, so I'm going to take a break from the science for a moment, and I'm going to talk about field mishaps because they're fun to talk about. So this is a sequence of stories that all happened in one location. So a couple weeks before my team and I went out to the field this year, Brian Jackson and his crew, a couple of his students, happened to be in the area, and they very nicely offered to set up some trail cams for us that would take images, I think every 10 minutes or so. And they would set them out for a couple of weeks so that when we arrived, we could have a look at the data and say, oh yeah, there's a lot of dust devils here. This is a great site to set up our instruments. Or no, there's no dust devils here. We really should go somewhere else. And so they went to this site, they took a lot of images, they set up their trail cams, and they went to great pains to show us where it was so that we could find it. And unfortunately, the one that we managed to pick up only got one image. We don't know what happened because I tested it and it worked just fine, but it got one image. And so we had no idea if it was a good site or not for dust devils. But we got a chance to get a feel for the dust devil activity at that spot because, oops, let me go back. We came along this road, picked up the trail cam, which was right here, and drove on and promptly got stuck in sand right here. And we couldn't go anywhere for the next day until our friend came to bail us out. So we saw a nice sunset. We camped up on the ridge there and we didn't see any dust devils. And so we concluded that that was not a very good site for dust devils. So maybe that was a good thing. Our friend who came to bail us out, he towed us out, which was fantastic. But on the way down to meet us, his transmission went out. And so here we are. This is a picture of us kind of, babying him as he drives in front of us on the way to the nearest town so that he could go and get his clutch fixed. And he was actually a couple days late to our actual field site that year this year because things happen, things just go wrong and you just got to deal with it. So that's mishap number one. I will have two more of these, one in the middle of the talk and then one at the end so that we can have little breaks and maybe hear some funny stories. Okay, so back to the science. So there are a lot of dust devils in places on Earth. So the question is, are they important? Do they mean anything for weather or climate? Well, for a long time, meteorologists didn't really think too much of them because most people don't live out in the desert like that. So who really cares? But a study came out in 2005 that suggested that, yeah, maybe there was a lot of dust being wafted by these things and maybe we should pay more attention to them. Maybe it even is responsible for lifting about half the dust that you see, because there's little dust devils going on all the time all over the Earth, whereas dust storms are just a once in a while kind of thing. And then more studies came out, people did a more careful look at it, and about 10 years later said, no, dust devils lift only a tiny fraction of the dust, you don't really have to worry about it. And then more studies, some that were done before that and some that have come out since, have said, well, yeah, they really can be important, at least on a regional scale. So yeah, they are something that we need to think about. So they could be very important for air quality, at least locally, temporarily, and they might all add up together cumulatively to impact the climate. We just don't really know. And since they transport a lot of dust, they loft a lot of dust pretty high into the atmosphere. That could impact ecosystems. Sometimes dust is harmful to life around, and sometimes it brings nutrients. So these are things that really need to be looked at. So there are things we understand about dust devils. We understand what it is required to form them. So first of all, you need a good sediment supply of loose, dry, really fine grained dust, like we're talking micron sized. You need a wind that isn't too strong, it isn't too light, but a moderate wind. And you need a super adiabatic lapse rate. That means that the surface is a lot hotter than the air above it. So you need a temperature contrast. It's kind of like if you want to boil a pot of water, you heat underneath it, and then you get boiling because you have this really hot surface and water that's not quite as hot. So that contrast is what makes for the boil. We also figured and thought, and this is part of what I wanted to look into, that the dust devils might change their character or the likelihood of formation based on local topography or how bright the surface was or other surface properties like the roughness or how like the heat capacity of the surface and other weather patterns that come and go. But that's not something people have looked at into greater detail yet. There are also dust devils on Mars, and this is my heart and joy. We think that dust devils on Mars are very significant. They might contribute to more than half the dust load in the atmosphere. They're going on all the time some more on Mars, just like they are on Earth. And Mars has really amazing dust storms, but they also have really amazing dust devils. So I think the Mars scientists are perhaps paying a little bit more attention to dust devils than Earth scientists are because they have to. So dust devils have proven useful. A couple of missions have been extended. They've had their lives extended because the solar panels that power them get covered in dust over time. But once in a while, a dust devil will come along and brush away that dust and give them more power. So the Opportunity mission that landed in the early 2000s and just ended a couple years ago, it probably never would have lasted as long without dust devils. And also, finally, dust devils might be trouble. If we want to send people to Mars, we need to think long and hard about our microbes, the little life that we bring with us. We just can't help but bring it with us. We try our best to be clean, but if people are going, we're gonna breathe, we're gonna release bacteria into the air. It's just gonna happen. And if the dust devil comes along and whips one of those away, and it happens to survive long enough to reach to an environment where it might just survive, then we might contaminate ours. So understanding dust devils is something that we really need to do before we send people to Mars. So there's a lot of dust devils on Mars. The video I was showing you before, this is from Spirit, so this dates to the early mid 2000s. So this is in 2018. This is a video from Curiosity. They've been seen by almost every single lander on Mars. There's one that has not seen them, but it has detected other signs of them having passed. So they happen every day almost. And here's an image of dust devils from orbit. So they're big enough on Mars. Some of them are just huge that they can be seen from orbit. Here's 4 of them. So the white patch is the dust plume that's lofted off the surface. And then the black line here, this is its shadow. So you can calculate its height by measuring its shadow length. And this area is right here in this box. So this whole image is just covered in dust devils. This is an image of Amazonas planitia, which is the dustiest part of Mars. So some of these dust devils are big enough that you can see even from this scale, but a lot of them are small, and I've marked them off with these yellow dots here. So there's quite a few here. So our study, what we were trying to do is understand what affects dust devils. So to be more formal about this, we design an experiment where we take instruments out into the field. We set them up in a particular place. We measure lots and lots of things about the atmosphere, like its temperature. I'll show you in a little bit. And then we just let things wash by. We let the winds come by. We let the weather come by. We let the sun come up and go down. Those are our independent variables. Those are the things that vary in the course of our experiment. And then there are the dependent variables, the things that we're trying to measure, that we're trying to understand. Things like what time of day did the dust devils get started? How many are there per unit area? What is their shape? Are they more funnel shaped? Are they more cylinder shaped? Does that vary with time, with space, anything, with weather patterns? And there are spatial patterns. How high did they get? How wide are they? Does that correlate with anything? And nobody really knows. There's a lot of modeling studies that have proposed ideas, and many of them conflict with one another. So this would really help to nail that down. So really what we want to get at is, can we then take those correlations, those relationships that we find, and use them to study the atmosphere? So can we look at those images of dust devils on Mars and say, aha, I know what the weather was like there because the dust devil was this big and this far from its neighbor. That would be ideal. And it's never, science is never that simple. It never provides that easy an answer, but we were trying to go in that direction. So I'm going to introduce you to my field site. So we went into the middle of Nevada, into the Basin and Rain province, in a valley called Smith Creek Valley. We were there for a couple of weeks in 2019 and a couple of weeks again this past June. Here's a zoom in. Let me see here. This square right here. I'm going to zoom in right there, and that's it. This is Smith Creek Valley right here. These green things are mountains, and this here, this is the playa, and this is where we set up our instruments. So it's a pretty long valley, 64 kilometers long, and I don't know, 12 to varying, depending on how you measure, 10 to 20 kilometers across, give or take. And the playa itself is not that small either. It's about 11 kilometers at its longest and about 5 kilometers wide, oriented kind of southwest, northeast. And it's at an elevation of about 6,000 feet. So it's pretty high up. And again, I'm sorry, I keep saying this. I'm zooming in on this little rectangle here. And this is the edge of the playa. And right here is where we set up our weather tower. So here's our weather tower. I'm going to talk about 2 suites of instruments. One is what I call team convection, and these are the meteorological instruments. So here's our weather tower covered in lots of instruments that I'll talk about in a little bit. Here's a ceilometer. This is an infrared laser that shoots to the sky and measures anything that crosses its path, and I'll talk about that in a bit. And we also had some smaller, more simple weather stations that we put up in the area as well. So here's our beautiful weather tower from which we measured temperature and wind profiles. We measured everything that we could think of. The wind direction, the air pressure, the humidity of the air, how much sunlight was radiating down on the surface to heat it up, what the surface temperature was, and then underground, because how the ground absorbs the solar heat also impacts how hot the surface gets. So the soil heat flux and the water content, which also impacts that. And so from those things, we can understand what we call the mean state variables. So the pressure, the temperature, the wind speed. We can also back out other factors like surface roughness and the stress that the wind puts on the surface, how bright the surface is, and how the surface retains heat. We also had one very special instrument. So I want to say that all these instruments, we took data at 0.5 hertz. So that's every 2 seconds. But this one that's shaped like a claw, this took data at 20 hertz. And what's special about that is it lets us capture really small fluctuations in heat and in the wind. And from that, we can calculate how turbulence, all those swirlies that are invisible to your eye, but are happening all the time and are deeply related to dust devils, how strong they are and what's going on with them. So we had lots and lots of wonderful data. Here's the oscillometer. It's a infrared laser that gets pointed up so you don't see it. It's eye safe and it won't hurt the planes going by overhead. And it's a continuous beam, so anything that crosses its path over time, you're going to see. And so I'll show you data in a little bit, but you just get this constant stream of information, and it's really cool. So from that, what we wanted to get at was the boundary layer height. Now, if you remember, this is the boundary layer, and this is the height that we wanted to measure, because the height might relate to the size of the dust devils. So here's our site again. We have another instrument suite. That is what I call Team Paparazzi. So those are 4 cameras that we set up here. So here's our weather tower, and we pointed the cameras at the weather tower. And so here are their overlapping fields of view. So each of these triangles is what each of these cameras sees. We overlapped them because we wanted stereo data from which we could then figure out where the dust devils were. Kind of like your eyes use parallax to see how far away things are. And we took data with those wonderful cameras, 20 megapixel cameras out in the field let's see, we took data every 20 seconds and they were synchronized so that we could get time-lapse stereo. And I don't think that's something that's ever been done automated before. So each of these things that I've described, people have put weather towers out before to do dust devil studies. They've used stereo imaging. They've left out cameras to take time-lapse. But I don't think anyone's ever put it all together like that before. Really what I wanted to do is the mother of all dust devil studies, just throw all the data, get all the data, throw out all the instruments and see what fell out. So Team Paparazzi can tell us a lot about the dust devils with the images. Looking at a single set of images from one camera, we can learn things like the onset time in the morning. We can get the density, the number density, but using the stereo data, we can get the locations. We can start to look at the 3-dimensional nature of these things. We can get their width and their height and their tilt, all sorts of great things. So here's one image from our camera. This is a textbook day, and I'm going to talk a lot about this day, the 11th of June, 2019. It was a beautiful day. There weren't very many clouds in the sky. The entire day we had data. The entire day nothing broke. Nothing ran out of power. And there were a lot of great dust devils. It wasn't always the case. So the weather tower is off that way, a few kilometers. You can't see it in the images because it's too far away. Now I'm going to show a time lapse that day. All right, so we set up the cameras and turned them on at about 9 a.m. And for a couple hours, nothing much happened. And this is data. This is meant to have a wide field of view and to look as high in the sky as possible. So this isn't meant to be pretty. So we won't have any nice zoom ins on really dramatic dust devils here, but you will see some activity. There it goes. There's some popping up. They come and they kind of move to the left or right based on how the winds are going. And every once in a while, you'll see a plume from a car that zips by. I point them out when I see them. You can see dust devils way off in the distance. Sometimes they get close. They come and they go, and they come and they go. Let's wait. What else we can see? There's one. See the clouds moving by just to prove that time is actually passing. It was kind of a boring day, honestly. Now later in the day, things get a little interesting because the dust devils take on a different character. They're no longer this beautiful column, but they start to look more like wing gusts. They get stretched out. Let's see that soon. There they go. There's some. You start to see them when they're stretched out like that. They kind of take on this swoopy appearance. And that's something we'd like to understand better. So I'm showing you this for a reason, because coming up is a day that was not a textbook day. That was a car coming across. And then that last bit was the inside of one of our cars. And now I'm going to show you field mishaps number 2, a non-textbook day. So let's have a look at the other day. So this day started out with lots of dust devils. And notice those clouds in the sky, watch them. They're gonna get bigger. We're surrounded by mountains there. And on this day, every single mountain had a thunderhead, and they got bigger and bigger, and then they coalesced, and they rain fell, and then the dust devils shut down. So there's no dust devils during there's no dust devils during thunderstorms. And then it sent out this big plume of dust, and it rained, and it got dust smattered all over the camera lens. And then it went away, and the dust devils came back. But you know what? Then the storms came back, and we decided to take the cameras down. So, oh yeah, I have another movie because I wanted to show you what this looks like from the ground. We were there for that. This one. So I hid out in one of the trucks. Not everybody did. So this is in the midst of that dust that you saw overtaking the camera. But keep an eye on this bush because I'm going to show you some frames from that I took of that bush. Just looking around at our campsite. All right. So this is the same view. Make this big again. And turn like this. That's really annoying. All right. This is the same view from the same exact camera, different day that I showed you before. So not a textbook day, like I said. So sitting in the truck, I put my camera or my phone and took pictures with its camera up against the window, and I just left it in that spot, and I took a picture every once in a while. So it got pretty thick that we couldn't see out. It actually got dark for a little while. So I could sympathize with the Opportunity rover, which died in the midst of a dust storm. I feel its pain. And after a while, maybe a half hour or so, it started to clear, and there's that bush. Eventually it did stop. It was actually kind of cool because in the lee of a truck, we could see this swoopy wind streak. So that's kind of neat. So you can do science even when things go wrong. And my binoculars, they will never be the same. Okay, back to the science. Okay, so we have a lot of data. We took a total of 7 terabytes of data, give or take. So I'm not going to show you all of it. I haven't seen all of it. That's just too much. So I'm going to focus in on one day, that perfect textbook day, the 11th of June, 2019. So I had my grad student, well, someone else's grad student, Taylor Dorn, go through each of the images from one of the cameras and count up how many dust devils he saw in each frame. So that's what's plotted as the pink dots, the number of dust devils per image as a function of time throughout the day. So we set up the cameras just before 9 o'clock, and we let them go throughout the day and took them down about 7 o'clock. So The black line is the average of the pink numbers every 15 minutes. So the first dust devil we saw that day happened at 10:22 in the morning. And then the numbers rapidly increased, and there was this huge pulse in dust devils that lasted about a half hour just before noon. And then there was this lull until about 2:30 to 3 o'clock. And then there was another fairly big pulse, maybe not quite as big, but still noticeable. And then it kind of dwindled after that, and then eventually they stopped. So what's going on? You saw that there was nothing going on in the sky. It was perfectly blue skies all day. So what's with all the scatter? Why did it go up and down? And that's something that I'm going to try to explain in this talk, or at least put forth a hypothesis. It's really tough to tell is the answer. So that's the TLDR. It's tough to tell, but we think we might have a story. So let's step through a little bit of the data. I'm not going to show you all of it. So up at the top here, we have a dust devil to show you that this is the dust devil counts over here. So this is the plot I just showed you. And then down here is the ceilometer data. So this thing is the one that has the laser beam that shoots up into the sky. Anything that intercepts that laser beam reflects light back down to the detector in the ceilometer. And so that's what we're seeing. So this is height here, and this is time. So we turned it on at about 8 a.m. that morning as a power hog. We couldn't keep it on all the time. And the colors correspond with the amount of stuff that was reflecting its light back down into the detector. So the white dots are what the software that came with the ceilometer thinks the boundary layer height might be. So just a reminder, this is what we think the boundary layer does during the day. And in a nice idealized day where skies are clear, just like we had on this particular day, the boundary layer goes up because convective motions push it up and dust devils form. And that's pretty much what we see here. We see the convective boundary layer going up. And these yellow columns right here, those are probably dust devils or dust plumes, at least, that intersected the beam of the ceilometer. So we see them, which is cool. So here is the first pulse. You can see that happened right as the boundary layer shot up really quick. So that kind of makes sense, you know. Things are changing rapidly. Suddenly you get idealized conditions for dust devils, and dust devils are happy to form. That's great. And then something happened and they kind of stopped forming. And then here, just before 3 o'clock, we see more intersecting that ceilometer's laser beams. So it's nice to see a consistency in two different data sets. So it's real. It really happened. There were more dust devils, and there were fewer, and then there were more again. So let's look at some other data to see if we see anything that correlates with that rise and trough and rise again. So this is insolation. This is the solar irradiance hitting the ground. So before the sun rises, it's 0 because you don't see the sun, and then the sun rises and it goes up. So these dips here are because there were clouds early in the morning before we turned the cameras on, and then the clouds went away. And you can see that this curve rises. It peaks a little bit after noon when the sun was at its highest point in the sky, and it comes back down. So these little dips here are from shadows in the weather tower that passed over the sensor. So you can't avoid that. We did our best to limit it, but you can't get rid of it altogether. This little peak here is probably from our truck headlights when we came out at the end of the day to pick up the data. Nothing is perfect, but at least we know what it was. So the point here is that it rose and it fell. It was a nice clear day. Clearly there were no clouds. There was nothing going on that was obviously correlated with the dust devil activity. So let's look at something else. It's not the sun. Maybe it was the wind. So here is wind speed. So these are averaged over 1 minute. And then those again are averaged over 15-minute intervals. I realize now that I labeled that wrong. So here's wind speed here, and here's time again. So the winds were pretty light, and then they rose throughout the afternoon. These dots here are the wind gusts at that time. So the wind gusts were pretty strong, and they rose a little bit too. But again, it doesn't happen in a pattern that correlates with the dust devils. So what's going on? It's not the wind speed. And again, remember that these are from data that were sampled at every 2 seconds. We'll come back to that. That's important. So maybe it's the temperature. So here's a plot of temperature. The black line is ground temperature. This is in degrees centigrade. And then these other colored lines are from sensors higher up on the weather tower. So 0.5 meter, 2 meters, 10 meters. During the day, the ground is really hot. Air near the ground is also pretty warm. And then as you go up, the air gets cooler and cooler. And that's exactly what we measured. But again, there's no correlation with the rise and the dip and the rise in dust devil activity. So what's going on? It's not the temperature. So I'm not going to show you all my data. I have too much to show you. So I'm going to give you what we think is the answer. There's a parameter called turbulence kinetic energy, and it's really energy per unit mass. So those of you who have studied meteorology might understand what this is. If not, just think of it as a measure of the intensity of the turbulence. So all these little motions, not the mean wind that was measured at every 2-second intervals, but the little fast-paced wind variations that are measured at 20 hertz intervals by this beast. So this is the TKE, the turbulence kinetic energy over time. And you can see that as it goes up, so does the dust devil counts. As it goes down, so do the dust devil counts. And as it rises again, this little peak here actually corresponds with that peak. And then these guys here, these 2 peaks correspond with that. So this is the only thing that actually really correlated. And you can even see that as they come down, there's a drop in the TKE and then it rises again. And that probably corresponds with this little bump here. So it's not the mean wind sliding by, but it's all the little fluttery things going on. That's what probably caused this second bump in dust devils. So we spent some time doing some atmospheric modeling and looking through data. And here's our story. We think that it has to do with what was going on above the boundary layer. So the water vapor above the boundary layer does this. So along here is the west coast of the United States. And what you're seeing is goes west water vapor detections. This little red spot is our site right here, our field site. So in the morning, let's see, get back to morning here. There, 4 a.m. And then into the morning, you see it gets dark. There's this dark stripe that passes over our site. And then that's replaced by a bright stripe. So there's dry air that passed by overhead, and that was replaced by moist air that passed by overhead. And we think that that change, it was the change from dry to moist air that did something, that got translated down into the boundary layer. It's not so much that it was dry and that it was moist, but that it changed from dry to moist. Where that it changes, there's going to be a lot of activity. Some air is going to be more dense, some air is going to be warmer, colder. Moist air is more buoyant than dry air. So there are going to be motions at lots of different scales. And so at that transition, there's likely to be a lot of turbulence. And it might not show up in the mean wind measurements, but it probably shows up in the turbulence. And that's probably what we saw. So I have plots of some of the data that we found that we actually measured that do correlate with this and that do make sense. But I'm not going to show you unless you ask, because you've probably seen enough plots for me tonight. So I'm going to summarize, and then I'm going to go into my last mishap story. So what we learned about dust devils so far from this study. More solar irradiance, more direct sun really creates dust devils. We knew that. That's not something new, but our data supports it. Shocking. What we really learned is that dust devil production is really complex. It's not something that's simple to understand. We suspected that dust devils were sensitive to changes in surface properties. So if you have a brighter surface, it's not going to heat up as much. It might be harder to make dust devils on that surface, regardless of how strong the wind or how turbulent the wind is, or how much loose dust you've got lying around. We know that dust devil production is sensitive to weather patterns. Again, this is something that people knew. If you're having a thunderstorm, you're not going to see dust devils. But what we found is that it's also sensitive to changes in turbulence as the weather changes from one state to another. And I don't think that's something that's ever been reported before. So our next steps, I've talked about one day. We kind of done a deep dive into one single day, but we took data for many, many days. And that's a huge data set to go through. So I want to find out what correlates over the entire data set. So something like principal component analysis, where you say, all of these numbers and all of those numbers, what correlates? What set of conditions add up to make a dust devil rich day or a dust devil rich period, and what doesn't? And also we Haven't done any of the stereogrammetry yet, so that will tell us where the dust devils are, how big they are. Why do you get lots of little ones or just a few big ones? What conditions produce that? So we will get there. Okay, ending with field mishaps. So this isn't so much a mishap story as just a pretty collection of some of the friendly wildlife that we saw when we were out there. So pretty picture, pretty flowers, some footprints, from some furry woodland critters that kept trying to steal our food. Grasshopper, let's see. Did you know that scorpions fluoresce under ultraviolet light? If you didn't know that, next time you go out into the desert and camp, bring a UV flashlight with you. You'll find them. It's really cool. Let's see. Oh, and the one itty bit of a mishap that I wanted to end with here. Between our campsite and the one town that we went to for supplies, for laundry, for showers, for ice, gas, that sort of thing, there was a long road through a ranch, a couple of ranches really. This part of Nevada has open range grazing for cattle. So they would come up to the road and sometimes they would walk across the road. And one of our members, I won't say who it wasn't me, but one of the other members of our group was driving on that road late at night one night, and it was dark and the cows were dark and they were on the road, and one of the cows didn't make it, got hit. We had to call the sheriff. The sheriff called the local rancher. The rancher was fine. He said that this sort of thing happens all the time, and he's going to get his insurance payout, so he's probably just fine. And he probably had some steak to eat for the next couple of months. So at the time it was kind of sad, but now it's just a cool story. That's where I will end, and I am very happy to take questions from anybody. Sure, yeah.
I'm going to start with what did you tell us what it's like to be inside of a dust devil? Have you been inside of a dust devil?
I've driven through some. You know, one of the pictures I showed was a really, really big one, probably the most intense one that we saw. And I was going to drive through it, but I chickened out. But I've been in little ones, and it just feels like wind buffeting you around. It's kind of fun to drive through the little ones because you think you're going to disrupt the dust devil, but you don't. They just kind of ignore you, even the little ones. That's a good question.
Yeah. Did you happen to measure the humidity at your field site?
Yes.
Did you see any strong correlation between?
Thank you for asking.
Or if you saw
I have a slide for that.
Oh, perfect.
I didn't want to show more plots, but I've got them. Yes, so the things that we saw that were consistent with that dry air being replaced with the moist air were the ceilometer data. So up here, we have more reflections from the dry air and then fewer reflections from the moist air later on that kind of brushed it aside. And you can kind of see that kind of correlates with the same time that the dust devils came and went. So at the bottom, what we measured was relative humidity, because that's what sensors typically do. But relative humidity is affected by the temperature. So if you do the water vapor mixing ratio, which you can calculate knowing the air pressure, it kind of takes that out. So the brown line is the water vapor mixing ratio. So that's more, it's more like a tracer. So if it goes up, there's more water in the area, and if it goes down, there's less. So you can see where it goes down right around 10 o'clock. That's actually right around the time that the first pulse happened. So if you have dry air up here, dry air is more dense than what's below it. So that might have encouraged the overturning. That might have added to the energy of the very first pulse of dust devils. And then maybe it spent itself out. Maybe it just spent all its energy in that overturning. And so maybe that's what shut dust devils, really suppressed them for a while after that. And then let's see, where is it? Right around here, it bottomed out and then it started to climb again. And it was right around there that the dust devils picked up again. So we have moist air coming in. Again, moist air is less dense, so it's more buoyant. And so maybe that allowed dust devils to be more active.
It would be really interesting actually to see smooth the H2 mixing ratio, and then to see a time derivative against the occurrence, right? Because it does look like where the time derivative is big, that's where you tend to get these spikes.
That's
I don't
a really
know.
good idea.
I have no idea why.
I will try that. Thank you.
Yeah, that's an interesting result. Question here on the live stream: do dust devils turn into tornadoes? Are there tornadoes on Mars? And should you be studying those too?
Excellent question. Thank you for asking that. Dust devils are not tornadoes. So tornadoes form in thunderstorms, and so they get their energy from latent heat. So that's from all the moisture in the air changing phase from a liquid into, from a gas into a liquid. I think that's the direction it goes. So that doesn't happen in clear air where everything is pretty dry, like where we were. So the dust devils form all on their own. They will never turn into a tornado. You really need a lot of big energy for that, like you get in a thunderstorm. So Mars right now, and probably for the last several billion years, has not had thunderstorms because it's very cold and very dry relative to the Earth. So there's just not enough moisture to produce that kind of energy. But thank you for asking. That's an excellent question.
Another question here. You mentioned how dust devils are huge on Mars's surface. Is it the lower gravity or atmospheric pressure that enables them to reach such a size?
Excellent, awesome question. Both of those things probably don't hurt, but we know that the boundary layer on Mars is a lot higher. It can get a lot higher during the day than it does on Earth, and so that just means, okay, so the air is very thin, and so there's a lot more of a difference between the air temperature and the ground temperature, and so it makes it a lot easier for convection to become very strong. And so the convection cells that form, remember those spheres that got squashed into polygons that kind of hit up against each other and form these walls and these updrafts, the center of which form into potentially a dust devil. Those things can get really strong, and that can carry the dust way up high into the atmosphere. So that may be one other reason why dust devils are thought to be more important on Mars than on Earth.
Let's see, another question. On the topic of pollutants and dust devils, Nevada is known as a test site for atomic weaponry. Is radiation a concern or topic of interest when working in the field?
We weren't worried about it where we were, but I know that in 1990, maybe the early 1990s, there were a couple studies done by folks who were studying whether dust devils might pick up radioactive dust and carry it downwind, and whether that might be a hazard. And I never saw the results of that. I saw the scientific results of what they measured, but I don't know if it turned out to be a hazard. That might be classified. I really wish I knew the answer to that. So we weren't worried where we were, but it is something that has been studied in the past. Also a good question. They're all good.
Of course, there's interest in sending people to Mars. Will dust devils present a hazard to astronauts on Mars?
I think the air is so thin on Mars that if one passed over you, even one of the big ones, the really big, many kilometer tall ones, you probably wouldn't really feel it. So first, like if you're just standing there, it's not going to knock you over. So if you've seen the movie The Martian, the one big thing they got wrong is that the dust storm, they call it a sandstorm, the dust storm in the beginning, it knocks him out and it moves sand dune over him. It's not like that. They're just too thin. It takes years and years to move a big one. But dust could get into the crevices of the equipment. It could get into like the moving arms of the astronauts' suits. So I know that the moon dust was a problem for the astronauts. It got into everything. The moon dust, though, is really angular. There's no atmosphere on the moon to transport rocks that break up, and so they're incredibly sharp, teeny tiny little dust particles. Whereas on Mars, all that dust has been transported by the atmosphere and they've banged against rocks, and so they've been rounded a bit. So it would be a problem, but it wouldn't be as much of a problem as it would be on the moon.
Excellent. Well, thanks for joining us, everyone. Let me get you to unshare your screen there.
Yes. Yeah.
So thanks for joining us, everyone. Again, this is First Friday Astronomy for Boise State Physics. Join us again on October 1st, 7:30 p.m. When we're going to hear about dark matter. That'll be a really exciting talk. That will certainly be live streamed. Possible, although I think probably pretty unlikely at this point that will also be in person. I promise as soon as we can host these safely in person again, we will be very happy to host you back on campus. In any case, look for our next talk in the lecture series, October 1st. Have a great weekend.